Hello and welcome to the learning booth. So we have already 3 lectures completed. So let's start our fourth lecture of the series of structure analysis. In this lecture we will try to find out reactions of two complex frames. This example will definitely help you to find out reactions of any type of structure given to you. So let's move on to our first example. In this example we have a frame shown here. You can see it. Determine the horizontal and vertical components of the reaction at the pins A, B and C. So two type of information are given here. First, that we have to find the reactions at point A, point B and point C. The second thing is we have pin connection at point A, point B and point C. So here you can see that we have an internal hinge here. So this gives us information that our structure is divided into two separate members, or we can say it separate structures. So from the previous knowledge we can say that if we have two structures or two frames here, then we have the 6 number of equations or 6 equilibrium equations that can be used to find out the reactions of this structure. Also this frame have two different type of loading. We have point load here and we have also have uniformly distributed load here. We have different geometries, we have different arrangement of our structures. So let's find out the reactions of the structure at point A, point B and point C. So let's start our solution. First of all, we have free body diagram. So this is the free body diagram of the structure. Since it has internal hinge, so we consider them as separate members. First we will find definitely moment at point C and point A. That will yield us the point the moment at point A gives us the Bx and the moment at point C gives us the By. Now if we check, if we find out the moment at point C, the force Bx, Cx and Cy are passing through the pivot point. So we have only unknown force, that is By. So we can find By here. Now we apply these By here and find out the moment at point A. This will give us the point Bx, this force Bx. So now we will completely know Bx and By. So we can apply the other two equilibrium equation here, summation of vertical forces and summation of horizontal forces on this joint this member, and also we can apply the summation of vertical forces and summation of horizontal forces on the member BC. So let's check the solution of the question. As I have demonstrated in the previous slide, we will first find out the moment at BC structure. That will yield us By, vertical reaction on the B point of the structure. Then we have member AB. So on member AB we will have summation MA, that will yield us Bx. So we will find completely know here the joint B. Okay, these two reactions are of the joint B. Next is we have applied summation of vertical forces and summation of horizontal forces on the structure A, and we have AB, and we have find its reaction AX and AY, and then we have applied these equilibrium equation to member BC, and then we find the reactions of member at the point C. So these are all the reaction we have find from the structure. I thought that was easy. So let's move on to the next structure. This is our example 2. In this example we have a gable arch and wind load is acting to it. So let's read out the question. The side of the building in figure this one is subjected to a wind loading that creates a uniform normal pressure of 15 kilopascal. So we have this wind loading on this side of the structure. So let's mark the structure, this one. This side of the structure is subjected to loading. okay, directly wind loading. On the windward side, this is the windward side, and a suction pressure of 5 kPa on the leeward side. So we have 5 kilopascal on this side, okay, leeward side, the side against the wind side. Determine the horizontal and vertical components of the reaction at the pin connection A, B and C. We have a pin connection at A, B and the point C here, inward. So we have to find the reactions on these all 3 points uh, of the supporting gable arch. So here we can see that our structure is 3D structure, and in our analysis we only analyze 2D frames or 2D structures. So let's change it into 2D structures and find out its reaction. Here we have converted our frame to 2D frame. So as we have seen that load was acting on the 4-meter side of the gable arch, so we have multiplied the wind force 15 kilonewton per meter square multiplied by 4. That is 4 is the side width of the gable frame. So 60 kilonewton per meter is acting on point this point from A to this joint, and 60 kilonewton is also acting from A to B overall structure, and from B to C we have 5 kilonewton, that was section pressure, and we have 4 meter, that is the width of the gable arch. So we have multiplied that, and 20 kilonewton per meter is overall acting on this structure on the leeward side, and we have 60 kilonewton per meter on the windward side. So now we have to find the reaction at point A, point B and point C. Now it's easy that we will first divide this structure into overall 2 parts, because we have internal hinge in it, and we can also convert these uniformly distributed load to point load to make our structure or our equilibrium equation solution easy. So let's check the free body diagrams and then we will find the solution for the structures. So our free body diagram looks like this. We have overall frame. In this frame we have converted the uniformly distributed load to point loads. Here 60 kilonewton were acting, so we have 60 multiplied by 3, 180 kilonewton per meter. The length of this one is actually greater than 3, so we have 254.6 kilonewton acting on it, and other side we have 84.9 kilonewton was acting on it, because this frame is turned at 45 degrees, so we have length greater than 3 in it, so the greater force is acting on it. Now since there is internal hinge in it, so we have divided this structure into 2 parts. First is from A to B, and then other one is from B to C. So like the previous structure, we will find the reactions of this structure as well by solving the moment at point A and point C. So first we will sum the moment at point C and our point A. That's actually same. We have symmetric but different type of loading. We have symmetric geometry but different type of loading on both the structures. So let's check our solution. So this is our solution for the structure. We have applied the equilibrium equations on both the frames and also applied the equilibrium equation on the entire frame. So from the entire frame, when we sum the moment at point A, we will have only unknown force that is acting, is creating moment, is Cy. So we have find Cy from the summation of moment at A. Cy is equal to 240 kilonewton per meter square. We have the moment due to 180 kilonewton, we have the moment due to 60 kilonewton, we have the moment due to 254.6 and 84.9 kilonewtons, and also the vertical component of these forces also causing some moments as well. So we have find Cy from summation of moment at A. Now we find we will apply summation of vertical forces on this structure as well, entire structure. So we will find Ay from this structure. Now let's apply the member equilibrium equations on the member AB. So we have summation of moment at point B, so we can find force AX, BX, BY and CX in the same manner by applying the equilibrium equations to the structure. We have total applied 6 equilibrium equations on overall structure, because we have two different structures, because we have internal hinge, so that divide the structure into two members. So we have total number of equilibrium 6 number of equilibrium equations to solve the structure. So that's all for today's lecture. Thank you so much, and please like and subscribe our channel to give support to us, and please comment if you like the video. Thank you so much.